All right, so the next section of this chapter is all about conservation of energy. And we've essentially already looked at it with the loop-to-loop lab, and we say EI equals EF, right? The initial energy equals the final energy, because energy cannot be created or destroyed, only transferred or transformed. So that's where we're going to get a quick introduction of this section. This pre-lecture video, he goes into a couple different examples of any energy transformations and talks about how it becomes from one type or goes from one type to another type. So that's what we're going to be looking at. So 10.6 is all about using the law of conservation of energy. And again, that's simply that whatever you start with, you have to finish with, as long as the work done on the system is zero. So there's no work being done. We're in an isolated system. The conservation of energy absolutely stands true. So we can use the law of conservation of energy to look at a before picture and an after picture for the different types to look at isolated or energy conservation. So whatever change I have in energy is equal to the work done. But in an isolated system, there is no work. So whatever energy I start with, I have to finish with. So this is actually a little backwards. This is the initial case. This is the final case. I started with this. I end with this. The magnitude of those values are the same. Notice how in the final case, of course, there is some thermal energy added. So energy cannot be created or destroyed, only transformed or transferred. So transferred goes back to this concept of work. And in an isolated system, work equals zero. So we got a quick check. A spring-loaded gun shoots a plastic ball with a launch speed of 2 meters per second. If the spring is compressed twice as far, what will the launch speed be? Well, this is a perfect example of potential static energy, or elastic potential energy rather, becoming kinetic energy. This is going to be 1/2 k delta x squared, and that's going to be 1/2 mv squared. So it starts as static, or spring energy becomes kinetic friction. So if I double how far it compresses, I quadruple the amount of energy, which means I'm also going to double the velocity, because that'll quadruple the amount of kinetic energy. So it'll be from 2 to 4 meters per second. Another quick check, same concept, but now we're replacing the spring with a new spring having twice the spring constant. So again, I have US equals K. US is 1/2 k delta x squared. K is 1/2 mv squared. Now, if I double the spring constant, I double the amount of energy. So my velocity will go up by a factor of the square root of 2. And 2 meters per second times the square root of 2 is going to give me 2.82 meters per second. So the rest of this section just takes a look at some problems. So here we have a car sitting at rest at the top of the hill. It goes down the hill. Equation for the conservation of energy, solve for the velocity. So we start with potential energy, and we're still moving down the hill, but now we have kinetic energy. So we'll solve that during class. Another partner problem we'll solve during class. Now it's going down at a constant speed. So the height was 3 meters, and determine the amount of energy lost due to friction. So we have potential energy, and that energy is becoming, well, it depends on how we look at it. It could be becoming a little bit of kinetic energy and also thermal energy. And depending on how we look at this kinetic energy, we can either say that it was already there, or we could solve for it. That'll change our thermal energy. But again, it's a transformation from potential to thermal and kinetic. And we'll take a look at that tomorrow. The next one, we have same concept. We're going down a slide. The starting point's 9 meters above the ground. All I care about is my initial point and my final point. Starts with UG, ends with K, because the slide is frictionless, so there's no thermal energy. Very simple concept. UG, mghi, K, 1/2 mvf squared. Of course, as this happens quite often, the masses will in fact cancel, and I have VF equals the square root of 2ghi. that formula should actually look really familiar from kinematics. We've seen that formula before. But anyway, that's all we're doing. We're setting one energy equal to another energy. The rest of this unit is going to take a look at a couple different applications. We're going to take a look at energy during collisions, and we're also going to take a look at another way to quantify energy, but it's not quite energy. We're going to look at power. So we'll be doing those in the next segments.